the linear solution, and I focus today only on the linear solution, from the kth order series approximation. So actually, what I'm really doing is I just take Samuelson's fundamental approximation theorem to the portfolio choice problem and apply his procedure to solve these GE models.
His procedure was not Taylor's.
It was. It was.
He assumed a cubic utility function. And so
No. What he did is the first order condition for the portfolio choice problem,
Yeah.
and then he computed the second order Taylor series expansion in the shock terms about the zero shock. Okay, and from this
Why
he
did
got
he
the
have to
mean
solve
and.
a quadratic equation?
Sorry?
Why did he have to solve a quadratic equation?
No, he just did it in his example. He just said computer kth order Taylor series expansion, and then he did it up to second order, and this is the reason why he came up with the mean variance solution. I have it here. No, it's a nice time to be okay? No confusion here, thanks so much. Because this is actually the last talk, and I think we are all quite tired, so I would like to present a summary of the results, directly the advantages of just following this approach. At least I would like to argue that these are the advantages. So the theoretical implication of computing the AES approach, this approximated equilibrium system, is that the system itself is no longer stochastic. It is has a deterministic, expression. It preserves the nonlinearities in the endogenous variables, but it is now linear in the first k moments of the exogenous disturbances. I will show you later on what I mean by this. So I have now a new equilibrium system which preserves the nonlinearities of the endogenous variables, but where now the first k moments of the exogenous shocks enter as parameters. So then I can compute from this the linear solution, by which I mean the steady state and the first order Taylor coefficients, which now pick up the effects of risk locally, but which pick up the effect of risk up to the first k moments of the system.
You're using first order, but then you're talking about k moments.
Yeah.
Taylor series first order.
No, wait a second.
But k.
Wait, so, okay, this would have been the last slide, my last comment. But what I'm doing here is I disentangle the perturbation in shocks and the perturbation in the state variables. Okay? So,
Why would you do that?
wait a second. I hope that I somehow convinced you that this might be
I mean,
wrong.
Taylor's theorem for two variables does not do that.
No, wait a second. In shock terms. So if you really perturb in shocks about the zero shock vector, right? It's a singular perturbation. It is not a regular perturbation. Let's discuss it later.
It's a singular perturbation if you don't do it.
Yeah, let's discuss it, please. I would like to
Otherwise,
come.
making mathematical assertions that make no sense.
No, I would like to come to slide 4 at least during the next 20 minutes. Okay? I would just like to present what I'm doing, and then we can discuss things afterwards, or you can slaughter me afterwards.
You're making a lot of very negative comments about published papers.
Why?
Not exact. Well, I mean, I and others have done higher order approximations.
Yeah, I really appreciate this. This is just a proposal. It's just an idea. Yeah.
Well, and the others are bad ideas. Is what you're saying?
No, never ever.
You're saying this is better.
No, it's just a different approach. It's just okay. I tried to do my best. Otherwise, if you're going to slaughter me, it will be nasty enough with all my recollection. Okay, so third.
He does it for everybody.
Yeah, I know. It is not offensive. It's really not offensive. It's just my idea how to come up with a. Okay, let's forget about my ideas and just read off the slides. So the third theoretical implication that actually the approximation error to the linear solution is exactly of the same order of magnitude as the approximation error of the approximated equilibrium system to the original one, which is the same order of magnitude as the implied order error. Okay, so these are formal statements. I do not want to present them here because of time limits and my fear not to survive this presentation. Okay, what are the practical implications for researchers, which I would really like to emphasize? So the first is that we have a linear state space representation of the solution process, which now allows to study the equilibrium implications of nonlinearities in stochastic environment locally. Yeah. So that is the proposed approach captures the effect of risk up to the first k moments of your AES approach on existence, determinacy of the equilibrium system, on the equilibrium distribution, and also on the dynamics. So another advantage is that you can use standard linear econometric tools now to study these nonlinearities. Okay, and in general, it enables to use the linear toolbox to study risk in general macro models. For instance, welfare comparisons, asset pricing, DSG models, markup switching models, because of preferences, time varying, volatility. So all these things you could, in principle, solve with a linear state space representation. Okay? Or you can, a couple of these examples I computed. Second practical implications, again on accuracy, is that the accuracy of the linear solution with respect to risk increases in the order k of the Taylor series expansion to the equilibrium system. Again, it is only the Taylor series expansion in the shock terms, yeah, for any given state point in the state space. So again, this also increases the local accuracy of the existence, determinacy, equilibrium, blah blah blah. It also increases the accuracy of the maximum likelihood inference and hence parameter estimates based on this linear solution. So this is a result I take from a comment of Ackerberg and others on a paper about how the approximation error to the solution actually affects the likelihood. And in this case, just taking the result, the accuracy of the estimates using a likelihood procedure also increases in the order k. Similarly, accuracy of forecast based on the linear solution increase in the order k. Okay, the last practical implications, because it is just taking Samuelson's approach to solve DSG models, is that it is also applicable to models where the solution is not determined locally for the deterministic case, but for instance for the second order case. So this is the classical mean variance result. So you can use this approach to come up with a linear solution to the mean variance problem in the standard DSG model. So I can solve using this simple, at least in my view, simple approach, also a dynamic portfolio choice problems in a linear fashion. Okay, I survived slide 6. Come to slide 7, just the outline of the presentation. I give you the general formulation of the equilibrium framework, and then I would like to show you the solution procedure and how I actually implement it. And then I would like to discuss one application. I could have come with different applications, but I really focus on the asset pricing model for which a closed form solution exists, and for which I can really make my points I mentioned earlier, presenting some graphs and some figures, okay? And the related literature I would like to discuss at the end. Okay, so the general formulation of the equilibrium framework is that we have this stochastic equilibrium system where y is the vector of endogenous non-predetermined variables and s is the vector of endogenous and exogenous predetermined variables, so the state variables. So the exogenous state variables are given by this implicit formulation, where it is a bit more general than just having it in a linear fashion, but the main point to take here is that for the exogenous variables, you can actually use this separate formulation to solve directly up to k order the implications of the exogenous process in this shock term. Epsilon is the vector of IID exogenous disturbances, and I follow, for instance, your approach to use this sigma as the scaling parameter. So that means I use this scaling parameter as a perturbation parameter. I set this equal to 0.
Well, then how is it you get a singular perturbation?
Yeah, wait a second. So this is a sigma, and if this is 0, shocks obviously cannot enter the system, and we are in the deterministic case. And I'm going to use this perturbation coefficient to approximate the equilibrium system up to the order k. So the solution process is assumed to evolve according to the function g, depending on the state. So the endogenous, exogenous state variables for the non-predetermined variables, and the state variables follow the process k, which depend on the shocks, only because, of course, the exogenous law of motion depends on the shocks.
Why doesn't the y's? Why don't the y's depend on epsilon?
Y's?
The y's are endogenous variables. Or what?
Yeah, y's are the endogenous non-predetermined variables, and
they depend also on sigma.
yes, of course, but because no, wait a second.
They depend on sigma.
No, wait a second. Let's discuss this later on. What you are after is, I guess, that you're going to parameterize the solution in sigma, right?
That's what you've done already with sigma on the previous slide.
No. I haven't parameterized anything in sigma.
Yes, you did. You said that when sigma is 0, you have the deterministic model.
You can.
And you increase sigma.
Let us.
Parameter that you have.
Yeah. Can we discuss this, please, at the end when I come to the related literature? Then I give the correspondence between my approach and when you really parameterize the solution in sigma. It's just postponed.
What does that mean that you have a sigma times 0, but you're not parameterizing anything?
No. I do not explicitly parameterize. Wait a second,
So you're
please.
saying that the y is dependent only.
Yeah,
on
exactly. Okay.
Not the sigma.
Okay. If you can wait 5 minutes, I will show you what I mean, or if you cannot, I will just write it down. Okay, so somehow I have expected it. I don't know why. Okay, so here we have the system of the stochastic. We have the system of the equations determining the endogenous variables, and I just plug in the solution process for brevity and call this the capital F function, which now depends, given the solution for G and Q, on the current state and the exogenous disturbances. And for simplicity, I assume that all regularity conditions are satisfied. So then I compute, or this just states the kth order Taylor series expansion to the stochastic equilibrium system in the perturbation pyramid about the deterministic model, that is about sigma equals 0. Yeah? For any given state, this is just the Taylor series expansion in sigma. So this means that you have, when sigma is 0, the deterministic model. Because you expand about the deterministic model.
Wait.
Yeah,
You start with the steady state?
No. For any given.
So you start with the entire solution, global solution.
No. It's just the representation of. It's just the representation of the Taylor series expansion of the stochastic equilibrium system about the deterministic one. So if I start from the deterministic one for any given state, yeah, then I can compute from the deterministic one how the deterministic equilibrium system changes given that the sigma is slightly perturbed. And because the sigma is slightly perturbed, then of course this epsilon t plus 1 enters. So this is the first order condition, the first order Taylor term in sigma. Then the second order Taylor term enters, which means that because it is the second order term, you have here the variance covariance term. The third order term means that you have here the third moments, and so on and so forth. Okay.
What are you expanding it around? You're expanding it around the solution, global solution of the deterministic model.
Given the solution, I don't know what you mean by global solution. This is the solution. I don't know the solution. This is just the Taylor representation.
I think it's just the deterministic steady state.
Yeah. No, it does not. No. Wait a second.
I don't want to say that.
No.
It is for any initial condition.
It is for any, it's a general, so this is the stochastic Taylor theorem, and it is for any given initial state St. So, and the simple idea is, consider the case where you have just one exogenous variable and one endogenous non-predetermined variable, and you have this representation for the deterministic solution.
Oh, so you do know the deterministic solution is over.
Wait a second, just wait a second, please. It's my talk, not yet your talk.
I mean, you're making us.
No, wait a second, it's my talk, not yet your talk. So this is the deterministic solution, which is implicitly stipulated by the deterministic equilibrium system. So this is the deterministic equilibrium system, which implicitly stipulates the deterministic solution. What I am after is, I would like to compute an approximation in the shock terms, which now gives me, at least approximately, the implicit characterization of the true one, okay? So the true equilibrium system stipulates this solution, and what I'm after is, I would like to approximate the characterization, the implicit characterization of the solution process. Okay, so, and what I am saying here is, in this general statement, implicitly we get something like that. Or if I'm very good, so suppose only second moments enter and third moments they vanish, do not play any role, then I got the exact characterization, at least implicitly, of the solution. Yeah?
S is both endogenous states and exogenous states, right?
Sorry?
S is both endogenous
Yeah,
states
both
and
together.
exogenous states. So you're characterizing solution for any existing exogenous and endogenous states. So it's a global solution
For a given state,
with a
yeah.
deterministic model for all the different exogenous states.
Yeah. Mhm.
Right?
Yeah, exactly. Thank you. Okay, so in detail, because we have endogenous non-predetermined variables, and they have to somehow react to the shocks. Exactly what you said. So this means that I have the deterministic equilibrium system, and then I have the first order Taylor series expansion in the shock, which means that I have to keep track of changes in next period's exogenous variable and changes, because the next period's exogenous variable changes in the next period's response of the endogenous non-predetermined variable. This I have to keep track of. How do I do this? I keep track of this at the deterministic solution. Why? I perturb about the deterministic model, and I know that from the deterministic setup, I have to evaluate the change in the endogenous non-predetermined variables for the deterministic solution, because it's a perturbation about the deterministic setup. Similarly, for the second order term, I come up with this here. Okay? So, and later on, I'm going to use exactly this here as my second order approximation to the equilibrium system. You're completely right. I have to keep track of how the endogenous variables changes respond to changes in the exogenous term. But this is what I'm doing here. And how do I keep track of this? I have to keep track of this about the solution where I perturb around, which is the deterministic solution. Okay? And this I can compute. Okay. Similarly, the associated actual law of motion for the exogenous variables must be appropriately approximated by a k-order Taylor series expansion. Otherwise, you would have if you do not do it appropriately, obviously what you have is that higher order terms do not enter the system, whereas the equilibrium system with expectation terms take them into account. So they have to, of course, match. So then my approximated equilibrium system, which I would like to use and to work with, is now the approximated equilibrium system up to order k and the approximated law of motion. So this is my new equilibrium system, which is now, if you allow me to switch back, which is now nonlinear in the endogenous variables, so the nonlinearity is preserved, but which is now parameterized in the exogenous terms. So these exogenous terms, because I'm perturbed about the deterministic one, I can take the expectations operator through, and I only have the expectations of the exogenous parts, of the exogenous shocks. And now my new system is parameterized in the moments of the exogenous distribution. And this is a deterministic or non-stochastic setup, which I can solve. And I focus here really on the linear solution, because linearity is so parsimonious that even I can handle it. So what I have to do then is the first step is to compute the steady state to the new approximated equilibrium system, which is the standard definition here, and the first order coefficients to the approximated equilibrium system, which solve the following expression here. So this is again standard for computing the linear coefficients, but now you have to compute it from the approximated system, not from the deterministic one, but from the newly approximated system. And what I would like to focus, draw your attention on is that these here now, if you compute the linear coefficients by some general eigenvalue decomposition or whatever you do, you have now also the eigenvalue decomposition depending on the first and second and higher moments, okay? Which means that if I would like to evaluate the local existence and determinacy of the problem, I also take into account the effect of risk on the local dynamics. We will see later on, if I come to it in the asset pricing example, what this difference make. Okay, so implementation. The AS approach actually contains 3 steps. The first is for a given initial state, that is, take for instance the deterministic steady state, find the respective derivative for the deterministic solution. So this is actually taking here, I know for instance this here, this point, I can compute, and for this point I can compute the response of the endogenous non-predetermined variables, which I need in order to keep track, if I now perturb the system in the exogenous shocks, how the non-predetermined variable responds tomorrow on changes in the exogenous parts. Yeah? So then I can compute this. These will be numerical numbers. I plug them back into my approximated system. So the partial derivatives of the system with respect to the other variables are still in symbols, and I can compute the steady state from the approximated equilibrium system, just computing the fixed point for the symbolic expressions. And then, given my fixed point, and given the linear stuff here, the deterministic solution here, I can evaluate these terms in order to compute the first order coefficients. Okay? Yeah, sure.
Maybe a dumb question, but so you pick an initial state, then you take the derivative.
Yeah.
It depends on the state.
Yeah, that's true. So what I focus here on actually again is computing not the whole description of the equilibrium system, but I would like to use the approximate description in order to compute for a particular point the linear solution. Yeah. In principle, you could do it differently. In principle, you could do it if you know the solution for the deterministic solution for different points. You can actually use the approach to correct for these different points for risk. But I only really focus on the steady state, which I easily can compute, and then I plug on the corrections from the deterministic steady states here, and then I can solve for the changes in the variables, which is now the new steady state to the approximated equilibrium system, and then I can evaluate these guys here, and I'm done. So here are the details. So these sets have. No, I would like to save the details. They're looking as ugly as when I'm slogged. So, okay, so accuracy, I have formal statements, I have proofs that it increases the accuracy, and the accuracy increase exactly in the order of magnitude as the Euler arrow I'm going to make. I have a couple of examples computed this, so including the standard neoclassical growth model with endogenous label supplier, with Epstein-Zinn preferences. I got a linear solution for a dynamic portfolio choice problem. But what I really like most, is the asset pricing model in Burnside, which is a very simple setup where you have one exogenous variable, the dividend growth rate, and one endogenous, the price-dividend ratio, where a closed-form solution exists. And I can use this example to really compare my solution with a conventional linear solution with the exact solution. And I would like to take this opportunity to make 4 statements, to just show 4 implications of this setup. So I would like to look at the Taylor coefficients and the implied equilibrium distribution for my linear solution to the conventional one. I would like to show you the implications on judging on existence and uniqueness of the solution. I would like to give you the inference results if I take my linear solution and having the true solution as the data generating process, what the maximum likelihood estimates will be from the conventional approach and my approach. And if time allows me, I would like to compare to conventional second order approximation, because what I'm doing is really I'm picking up risk and nonlinearity locally. The solution itself is linear. And it's a fair point to argue that I do not capture the nonlinearities by having the linear solution in the state space. But I'm not really after the nonlinearities in the state space. I'm really only after picking up locally the effect of risk. Okay, so A. So what you see here are the Taylor coefficients. So this is the steady state for the dividend growth process. Price-dividend ratio, and this is the first order coefficients on changes of the price-dividend ratio when the growth rate changes. So you always get for different parameterizations the true value from the exact solution, my value, and the conventional linear one. And in brackets you see the mistakes, so the error compared to the exact true value. So in the standard benchmark case, so I make actually no mistakes, so no error relative to the true solution, whereas the conventional approach has an error of 1.4%. If you go up for high curvature, again, my procedure has only an error of 1%. Both for the steady state and the linear coefficient, whereas the conventional approach already has more than 20%. Again, so this is a byproduct. This is not because I would like to increase the accuracy of the linear solution. It's just a byproduct. I really would like to have a linear solution which is able to capture the effect of risk on the economic decisions. But it's a nice byproduct, I think. So for high persistence, I'm doing worse, still better than the conventional approach, but the mistake is fairly large. Interestingly, which you can solve, which you can prove formally, but interestingly, the properties of the accuracy correspond also to the equilibrium distribution, computing mean and the standard deviation. So if you compute from the linear solution the mean and the standard deviation, that is the equilibrium distribution, these approximation errors, they carry over, okay?
You could compute the derivative with respect to sigma, like mean price dividend ratio, and just see like what would your solution predict in the conventional one. So if I increase sigma, price dividend ratio is going to change, right? So this is.
But the conventional approach is independent of risk.
Okay, so sorry, right? That's true. Then
Yeah.
But yours would give us this derivative,
Yeah,
right?
yeah,
And
that's true.
And you know the true solution too, so you could just say like, do I match this derivative or not?
That's a good idea. I haven't thought about this. Yeah.
Well, that's easy to compare. I mean, you're comparing yourself to zero. So you're,
No, but
No,
he
no.
has the true solution.
Yeah.
Compared with the true.
I would like to come. I would like to come to this issue later when I'm going to discuss parameterization of. Okay.
oh, the true factors.
Okay. So what I like, I personally like most, is the implications of the procedure in judging determinacy in existence. So what I have here is a plot. It's exactly the same plot Burnside did. It's exactly the same plot Burnside did in his paper, where you see here different parameter specification for the time preference and risk aversion. And you see here the areas where conventional approach says whether the system converges, that is, the solution exists, or whether it diverges, that is, we have local indeterminacy. So the white area is where you have convergence, which is correctly detected by the conventional approach. Then you have correct divergence, that is, the system correctly detects that the system is indeterminate, and the whole black area is where the system makes a false statement about convergence. So the conventional linear solution tells me here that the system converges, solution is unique, whereas the true stochastic system diverges, that is indeterminate.
Was there a unit root in those things?
No.
No, so the eigenvalues were
Yeah.
strictly stable.
Yeah. Yeah, you can compute them algebraically, and they depend on the persistence and.
What are the disturbances in this model? Are they log normal?
Yeah.
Then the conventional perturbation approach is completely invalid because it's a singular perturbation, because by adding any small sigma, you're making the support infinite. And that is what Samuelson said you should never do. So the thing is that this is not, it's a conventional macroeconomics approach. To call a conventional perturbation approach does a disservice to perturbation theory.
Even if the support was compact.
Well, it depends on the size.
You need eigenvalues more than one.
Okay.
No, I'm just saying that we have the true solution, the global true solution, and then there's some discussion about we do this linearization, and the thing is that if perturbation theory says that if you're going to use regular perturbation methods, you better not have a singular perturbation, and so you.
But this is regular perturbation in the state.
It's not a regular perturbation. It's a singular perturbation because the support explodes infinitely. It looks out.
No.
Algebraically, but it's a singular perturbation because as you add any small stochastic parameter, the support of the random variables become infinite.
But this is now in.
You said that in his model he had.
Okay, I don't want to take a stand on this. So
yeah,
what?
I'm just saying that this kind of criticism of perturbation is.
No, this is not a criticism of perturbation. Exactly.
You got the wrong answer.
No. It is not. No, it is not. Quite the contrary. I would say use just linear perturbation about the second order AES, and you get it correctly, at least much better than if you do it about a non-deterministic setup. So this is my convergence region. So, and it looks much better. Yeah. So if you compute the local.
What's the radius of convergence?
Wait a second. If you compute the local characteristics, so if you judge the local existence uniqueness from the second order AES, where you take into account the effect of risk. So it's not about perturbation at all. It's just about which approximation to the model you take. Is it the zero order AES, that is the deterministic one, or is it the second order? It's not about perturbation per se. So then you've mistaken me. So I did a mistake. It's not about perturbation.
Whatever you're doing is still a singular perturbation in the sense that the support of the random variable explodes, right?
What I'm doing, but then your perturbation approach has exactly the same defect.
I always say the support needs to be compact.
Okay, and if
Yeah, but
Okay, so don't say I don't
no,
say.
no. But if this is very small, very small.
It doesn't matter. It's the support that matters. That's what the math says.
Okay.
Support is what
Yeah,
matters. That's what I say also. So don't,
Okay. No, you're right. Sorry for this.
compact,
But-
then the,
and small enough.
yes,
Then it's a regular perturbation.
just assume that the moments of
Can I
No,
proceed?
No, you don't. That is
Okay,
not
so
mathematically valid approach.
what I would like to take
Support.
from this slide is really that as long as risk matters for existence uniqueness, you at least partly can pick it up if you judge it from the second order or higher order AES rather than from the deterministic model directly. Okay? So now maximum likelihood estimates, that is, I use the exact solution to the model as a data generating process. And I have now for the different specification benchmark, high curvature, high persistence, the parameter estimates for the persistence of the shocks and the risk coefficient. As shocks, I have the shocks to the price dividend process, and also in order to avoid stochastic singularity measurement error. Okay, so then I just compare, so these are the true values I plugged into the data generating process, and for the benchmark case, so the AES actually picks up the values, whereas the conventional approach makes a mistake of 4 or 5%. Similarly, for the high curvature case, and what is really funny here again is it's the Ackerberg et al. Result in econometrica, where the accuracy of the solution actually translates in the order of magnitude of the mistake to the point estimates. And this is really what you can see here in this simple example, that the accuracy of the solution really is in the same order of magnitude as the errors of the point estimates. Okay, and the accuracy gain translate into the point estimates. So for high persistence, yeah, my solution is also makes a mistake, but nevertheless, it's still better than the conventional approach. And you do not have to impose higher order solutions in order to somehow pick up the effect of risk on these estimates, which would prevent simple linear econometric tools to study these models. So the last point here is really to make clear that I would only like to pick up locally, using this approach, the effect of risk. And this is not about having nonlinearity in the state space itself. And then my question was, when I plotted this here, just to compare to the conventional second order solution. I mean, conventional second order solution actually, the way you did it, or Sims or Schmidt-Grohe and Uribe did it.
I don't do it the same way.
Sorry, never say again this, the not to be named in this room. Okay, so I have the conventional second order approach, the linear solution to the second order AES, and the exequence. So the exequence is the black solid line. The linear solution is the red, so my solution is the red one, and the conventional second order is the blue one. First, there's the distance, so that the steady state, what I call the steady state to the AES, better picks up the distance to the true solution. But in terms of curvature, as you see, that also having it linearly seems to be a better fit to the true solution than having it non-linearly, because the non-linearity never really matches the slope of the exact solution. So what you see in the shaded areas, because I would like to control also for the sojourn time of the system, that is, we have the probability density here, 90% and 99%, so that in 99% of the overall time when you would let the system run, you're really in this area. And this is the probability mass that you are really, of 90% that you're in this gray shaded area. So for high curvature, it looks fine. Now the high autocorrelation, and this is really interesting because here you see that the conventional second order solution better picks up the change in the slope. Yeah, so the curvature is better picked up, but it is somehow shifted. So it is not aligned, but it is shifted. Okay. So then the question is it good or is it bad? Because I got, at least for my linear solution, on average, the slope better than the conventional second order one. But in terms, for instance, of accuracy as the implied Euler error, you see that having the second order conventional way, the distance between the true solution and the blue one is here small. It is here also small, but increasing. And I have sort of more or less a constant gap. And this is actually what you also see here for this computing the standard Euler error. For the benchmark case, high curvature, it's fine, but for high persistence, so the max and the average Euler error are larger for my approach than for the conventional second order. So in this case, for having high persistence of the shocks, it seems to be if the system is far away from the steady state about which I take the linear solution, then the Euler error becomes larger, and this matters. Nevertheless, what I'm after is picking up the slope, yeah, the linear slope. Here the distance is small, here the distance is small. I have an average positive distance. So what I'm after really is the slope effect. That is the effect how the system behaves when we have a change in the dividend growth rate. And therefore I computed the dynamic Euler equation, which is just the difference. So the sort of the difference, two time periods, what was it? The difference of the Euler equation, the Euler error about 2 time periods, so that I somehow net out the constant term of my mistake, and I better pick up the effect of the slope. And then actually the AES approach is again better than the conventional second order approach. Okay, in terms of picking up the slope correctly, at least first order, it does then better than the conventional second order. Not in the absolute term, but for the linear coefficient and the slope, it does better. Okay. So the related literature. I made a mistake. I'm sorry. The not to be named is okay. So the first I would like to address is the conventional second or higher order approximation to the solution. So the central difference, the crucial difference, at least in my view, is relative to your approach. And you really brought the idea to economics as far as I see it. So the way you do it is to use also this perturbation parameter, to also use the perturbation parameter. So you are the one who invented the perturbation coefficient for us. But what you do actually is to take the solution to be parameterized in it. And then you say, and this is the conventional, oh, did I do this? Sorry. That you compute the Taylor series expansion in the sigma term to the solution. I take it to compute the Taylor series expansion to the equilibrium system. So this is the difference.
Solution and equilibrium system are the same thing.
No, not in this way. So what you do, let me explain. What you do is then you perturb the system in dst and d sigma jointly. Okay? You do it jointly. You perturb it jointly in the state and in sigma. Yeah. So my argument is, this is a good idea, but if you do a parameterization of the solution in sigma, but first perturb the equilibrium system in sigma, is equivalent for having parameterized the solution in sigma, is equivalent of first perturbing in sigma and then perturbing in the state. Okay? So the only difference in this perspective is if you...
By the way, your comments here have nothing to do with anything specific about these models. It's basically you're talking about a Taylor series expansion in 2 variables. So let's say 2 variables x and y, and let's say you start with a case where x is 1 and y is 0. And you're saying that doing a second order approximation in x and y, that it's better to first do a second order approximation in y, and then with that do perturbation in the x's. That's right. That's what you're saying about. That's what you seem to be saying, and that's what you seem to be making an assertion about Taylor's theorem.
No, what I'm saying is, okay, if y and x are 2 components in the state vector, you're right. Yeah. What I say is that sigma is not a component in the state vector.
Well,
what I say
doesn't care. Mathematics doesn't care about those things. State vector and all that.
Okay, if it doesn't,
you're making mathematical assertions, and they seem to apply to the Taylor's theorem in general. That it has. The math doesn't know anything about the interpretation.
Okay, that's fine. So if we can agree on...
From using Taylor's expansion methods, what you're saying is true.
Okay, suppose math doesn't tell me anything here, and I'm free to do whatever I want to.
No. You say you're doing math better than other math. Anyway.
No, I'm not.
You're saying you're doing an expansion of some sort around some.
No.
And somehow
this
you're
is
saying that it's better that taking the expansion around the joint thing, it's better to do one and then the other.
no. I haven't said that this is better.
Well, you're saying
So I'm just a naive student who saw how Samuelson computed the solution to his problem. He took the first order condition and then he perturbed the first order condition in the shock. Yeah, and this is the idea I had just. I'm somehow lost. I've never said that this approach is better or.
what I mean that it's valid is that somehow that.
Yeah, but at least it seems to be that it has some advantages because it is a linear solution. It picks up some of the implications of risk and nonlinearities.
Some, but
I can prove formally that the accuracy in risk increases. This is a formal proof.
so you get a higher order accuracy,
Yeah, in risk.
higher order.
This is a formal proof.
So you basically you can get like when you do a fourth order expansion in risk, that's better than a third order expansion in risk, and this is even before you've only got linear in capital stock.
Yeah. So this is just redoing Santos.
No. You're doing Taylor. Is what you're doing.
No, in the proofs. The proofs are very cheap because I just take Santos.
Why is this also not a proof that if you're doing a Taylor series expansion, it's better to do fourth order in Y and first order in X than to just jointly do the two together? You haven't distinguished this from just how what your ideas could also be applied to any Taylor series expansion.
Yeah, okay. Let's suppose I would agree.
Yeah.
Then I would say you could do something, but the way I did it allows me to get a linear state space representation.
That's a matter of form.
Yeah,
What about-
but it's a
you say
useful
higher
one.
Accuracy. You say it's higher accuracy.
It's not about, yeah.
And Taylor's theorem says that if you want kth order accuracy, you have to have a kth order expansion in both variables.
Okay, now let me take one last try. I'll have before you're going to slaughter me. Okay, okay, just
Move
one.
on, move on.
Because that's accuracy on some fixed exogenous.
Yeah. Now the other part of this is where you do a perturbation around this deterministic solution. That's in Jinjud. That's basically pointing out that you should formulate this in a Banach space and do Taylor series expansion in a Banach space.
I do not criticize this.
No. I mean, what's the difference between this and what
Okay, yeah, okay. Suppose you do it jointly in the state space and sigma. Okay?
No. That's that other stuff. Now I'm talking about your perturbation or deterministic solution business.
Yeah.
Yeah. That looks very much like a Banach space perturbation. In the Banach space. So.
I'm not inventing the world in a new way.
No, I'm just asking what's the difference between that exposition and doing a Taylor series in a Banach space.
I suppose none.
Okay.
I think the next one is that when you evaluate the model at two different points, right? Because first, at the deterministic steady state, you get an approximation of the riskless decision rule, but you use it only to approximate future moments of the variables. And then, given these future moments of the variables, you approximate the equations, and you solve these equations. So then you evaluate the model at a different point. So when you get the second linear decision rule for your linear decision rule, it takes information from two points. That's one way of putting it.
Yeah, but in principle, the stochastic Taylor theorem I used is what is said. It's just that you have a Taylor series expansion in the functional form. So you have a functional space where you have the deterministic one. Yeah, that's. But this is nothing I invented. Sorry.
Yeah, but
It's true.
doesn't seem that you did not implement that. That's my point. You did not implement.
No. I only wanted to say, okay, if I take this representation and if I know a point from the deterministic one which I can use to compute the shift in the representation, in the implicit representation of the of the solution, I can use this. And from this on, I then compute the local solution to this approximated equilibrium system. You're completely right. Nothing else. Yeah, so related literature. So there are the. Oh, do I have time? So.
Dinner is at 7.
So I can stop here.
Point that out, yeah.
I can, in principle, I can stop here. So there are two other related literatures. So, for instance, we have proposals to approximate the solution about the stochastic or risky steady state. And there I would like to take Chaire, who in principle, so I'm now referring to the paper he sent me last year. I'm not sure whether there's an updated version. Where he computes the stochastic or risky steady state in actually the same way that I do it, in the way he takes the, say, second order equilibrium system, and then he computes the fixed point, but then from this fixed point, he again computes the implication, which I called from the deterministic solution. He then uses the new fixed point, plug it in here, reevaluates the changes from the deterministic one, and does it in an iterative manner. So he solves for a fixed point. I don't do this. So I have an argument why I would not like to do this, because he computes this again from the deterministic model. So he plugs in the approximate stochastic steady state, what he calls it, plugs it in the deterministic version, computes them back iteratively. It converges, I guess, sometimes, most of the times. But these solutions, so if you plug in here the stochastic steady state, it is no longer 0, and this is no longer the solution to this system, okay? So therefore, I save these iterative procedure. An alternative how one could improve, I guess, the accuracy, and here are experts on this, doing this much better than me, is instead of going directly from 0 to 1 in the perturbation coefficient, is just to chop it in steps, okay? Doing it stepwise. Also, when it comes to the first order coefficients, when the solution converged, so he has a stochastic steady state, which converged, then he just plugs it into the deterministic functional form again and computes the linear coefficients for this. Okay? So, and I use then the first order expansion in the state of the kth order AS. Yeah, I'm done. I'm really done. So then it is your paper, Pablo, where you solve the linear solution about the risky steady state using indeterminate coefficients. It again has a similar approach, but it's an iterative procedure, right? So as far as I understood it, you have to use it iteratively. And then issues might be robustness, convergence, and also implementability to estimation routines. And we really have potentially problems also with large systems. So I can use my approach for really large systems. As concluding remarks, everything is said. Only for one thing, I would like to actually again mention that I focused in solving for a particular local point. In principle, this setup or this procedure could be used to characterize for some points in the state space the correction of the solution for risk. Okay, and from this you could then compute in a global manner the solution for each point having it corrected for risk. So, but I really only focused here on the linear solution, on the very simple setup. Thank you for your patience and